Hi, everyone. Thanks for joining today's session. My name is Zaheen, and today I'll be talking about Pinterest experience and migrating over 10,000 Hive jobs to SparkSQL. So a little bit about me. I'm a software engineer at Pinterest. I work on the query platform team, and I've been working at Pinterest for 4 years, and I'm mostly focused on improving SparkSQL usability and performance for engineers at Pinterest. For our agenda today, I'll go over the specifics of our migration to SparkSQL. Next, I'll go over the migration challenges and how we tackled them. And then we will discuss about how we built an automated migration service to help us automate many portions of the migration. I'll then go over how we tackled migrating Hive jobs in code over to SparkSQL. And finally, I'll wrap up the presentation by talking about the custom changes that we introduced to Spark and the results of the migration. So in late 2019, there was a push at Pinterest to improve developer productivity. One of the biggest pain points engineers had at Pinterest was that Hive queries would take forever, and it would be hard to iterate when developing ETL pipelines and doing large-scale analysis. The query team began to look at how we could improve query performance. We evaluated both Spark and Hive on Tez. Ultimately, we decided to go with Spark as that was the direction the industry was moving towards. And also, we wanted to focus our efforts on a single execution engine, as we already had many Spark jobs running at Pinterest at the time. It didn't make sense to add a new execution engine, as it would mean less engineering resources on Spark. And in 2020, after deciding on Spark, we began manually migrating Hive jobs over to SparkSQL. We identified the major pain points of doing the manual migration and developed an automated framework to help automate much of the work. In 2021, we continued migrating jobs to SparkSQL and resolving blockers. We also, at this point, decided that Spark was mature enough at Pinterest, and at this point, we decided to deprecate Hive. Towards the end of 2021, we finished our migration to SparkSQL, and in the beginning of 2022, we began migrating jobs to SparkSQL in the code. So the whole process took around 2 years. For the migration specifics, Pinterest was on Hive version 1.2.1, and we wanted to migrate over to Spark 2.4. And we had over 10,000 unique Hive queries that were running on a periodic basis. Next, I'll go over some of the migration challenges we faced. So one of the first challenges that we encountered was testing queries at scale and with no impact to production. And by no impact to production, what we mean is that queries need to be tested in such a way that they do not impact any production tables, and also do not impact cluster resource capacity. The other thing that we needed to make sure was that Hive queries need to be compatible with the Spark 2.4 SQL syntax, and the last thing that was required for testing was validation. How do we know that SparkSQL run produced the right results and did not regress in terms of the runtime performance or cost? To facilitate making queries safe, we built a library called Tailor. Tailor allows you to manipulate both Hive and SparkSQL queries. Tailor is built using a Python library called SQL Parse. And what SQL Parse does is it parses the queries into an abstract syntax tree-like structure that allows us to analyze and manipulate queries however we want. So here's an example of what Tailor can do. It can take a query and rewrite the query in such a way that the query is safe to run. In this example, we create a new table that is based off the production table and rewrite the insert clause to insert to this new table. You guys may be wondering why we didn't use the Spark extension API and change the plan to make the query safe. The reason why we didn't go this route is because we needed to have the ability to create and run safe queries on both Hive and SparkSQL. And we didn't want to duplicate the code to handle each framework. That is why we built a generic library that handles both. I'll also later go over why we needed to run both Hive and SparkSQL for the migration. Similarly, we use Tailor to make sure that Hive queries is compatible with the SparkSQL syntax. Here's one example, and in this example, we changed a temporary table into a temporary view, as the temporary table syntax is not available on SparkSQL. The next thing we needed to do is validate that the test SparkSQL run produced the same output as the Hive run. And in order to accomplish this, we built a row order agnostic checksum function that would take in all the rows produced by a query and compute a checksum. We computed the checksum for both Hive and SparkSQL outputs and compared the results. If the checksum matched, we knew that the output was the same for both Hive and SparkSQL. We also wanted to make sure that queries on SparkSQL were not producing larger or numerous files. Large or numerous files can potentially affect downstream jobs. For example, a large number of files can cause more mappers to be produced, and more mappers can cause driver memory issues, as the driver needs to keep track of all the new mappers that were created. We also wanted to avoid larger S3 costs, especially with our bigger datasets. We determined it was not worth investigating issues where the difference between Hive and Spark output sizes was less than 1 gigabyte. Some issues we found were due to the query plans being different between Hive and SparkSQL, and as a result, the compression ratio being more effective. For example, sometimes queries on Hive produced a sorted result, whereas on Spark it did not, which resulted in better compression ratios for Hive. We also made sure that the Spark output file count was less than the Hive file output count, and if it wasn't, the query was rerun with a repartition hint that was equal to the Hive file count. The next thing we wanted to do was validate the runtime and resource usage of the job. Users would not be happy if we were to migrate their Hive jobs over to SparkSQL only to see that the runtime of their job has increased. In the scenario where the Spark runtime was greater than the Hive runtime, we would try to either increase the number of executors or increase the size of the executors as a first step to get the job to run faster. If this didn't result in a faster speedup, we would dig more deeply into the job, either by looking at the query plan or profiling the query to understand where the bottlenecks lied. In the scenario where the cost of the Spark query was greater than the cost of the Hive query, we would reduce the number of executors or reduce the size of the executors until we were less than or equal to the cost of the Hive job. And cost was computed by looking at the ratio of the node that the executor was taking up. So for example, if an executor is using 24 cores from a 48-core machine, then it would be using half the cost per node of the node per hour. To help facilitate mass testing and validation of Hive jobs on SparkSQL, we built a tool called the Automated Migration Service, or AMS for short. AMS takes a state machine which contains the logic for your migration and executes it. It was built using Apache Airflow, and there sits a UI on top of it that reports the results of the test as well as the current migration status of the job we want to migrate. So here's a diagram of how AMS was architected. We have a query ingestion job that ingests new Hive queries and pushes them to the AMS database. We have a trigger DAG on Apache Airflow that would check for all the queries in the AMS database that were in the new state and trigger the state machine runs. The state machines are essentially parameterized workflows that are written in Apache Airflow that run with a particular set of parameters. Once a job has been migrated, the scheduled query checks if the job is migrated in the AMS database and automatically reroutes it to use SparkSQL. So in this diagram, we describe how the state machine of the Hive to SparkSQL migration was architected. All jobs start in the new state, and in this initial state, this is the initial state of the state machine. An AMS worker or state machine DAG1 will pick up the job and immediately transition the job into the run SparkSQL state. In the run SparkSQL state, the worker will query the AMS database and grab the Hive query we are going to run. It will call two functions on the Hive query. The first function call will make a call to Taylor to translate the Hive query over to SparkSQL. The second function will manipulate the query in order to make the query safe. The worker will then launch the SparkSQL job on Yarn. If the SparkSQL job fails and we know what to do, the AMS worker will parse through the diagnostic logs and give the run a failed reason and update the Spark configs as required. The job will then be re-executed with the updated configs, and a new run entry will be created. There will be a maximum of 5 retries before the job is sent to the fail state, along with the failed reasons. And common failure reasons that we encountered included things like out-of-memory errors, broadcast timeout issues, and S3 connection pool timeouts. If the SparkSQL job failed and we don't know what to do, we will transition the job to the failed state and provide a failed reason for the run. If the SparkSQL job succeeds, we will update the run entry with the total runtime, vCore usage, and memory usage of the job, and transition the job over to the validation states. So the first validation state is the output validation state. After a SparkSQL run has been successfully executed, AMS will move the state to the output validation state, and in there, it will launch a series of Hive jobs to compare the output of both the Hive and SparkSQL queries. The AMS worker will update the database with the stats from the checker. And the output validation checker checks for things like data size in bytes, the number of files produced, and the checksum of the data. If the checker fails due to data equality, the state will be transitioned to run both the test on Hive and SparkSQL simultaneously. We do this because sometimes inputs change between our test run and the original production run, and we need to run both Hive and SparkSQL at the same time in order to make sure that the input tables are consistent between the two runs. If the check fails for any other reason, the state will be transitioned to the failed state along with the failed reason. If the check succeeds, the state will be transitioned to the performance validation state. During the performance validation state, we will make sure that the runtime of the query is less than or equal to the Hive runtime and the total query cost is less than that of Hive. In the scenario that either one of these fails, we will try to either increase the performance or decrease the cost. If we are unable to optimize further, the job will be moved to the fail state, and the engineer would have to manually tune the job to make sure that it performs better than Hive. After the job passes both the output and performance validation states, the job is considered ready to migrate. And in the ready to migrate state, the user is provided a report of how the job performed on SparkSQL and given an option to migrate. Once migrated, the job will start running on SparkSQL. We also had a button available to users who wanted to roll back their jobs to Hive. This was provided as an option in the scenario where the user job, for whatever reason, failed on SparkSQL after we migrated. Jobs were put into the needs review state if we were unable to make the job consistent with Hive. In this case, the user is presented with a reason why we were unable to match Hive, and the user is given an option to migrate regardless. There is one other state that is not mentioned in this slide, and that is the deprecated state. The deprecated state allowed users to notify us that a job was no longer needed. Large migrations like this one are a good time to prune jobs that are no longer required, as you have someone looking at every single job. In order to make sure that AMS jobs were not stealing resources from production jobs, AMS test jobs were only allowed to run on the ad hoc cluster. Additionally, there was a queue set up for the ad hoc cluster to make sure that the AMS test jobs were not consuming large amounts of resources. We also limited the amount of test jobs running concurrently to 30. As you can imagine, running all these queries on a new engine can cause a lot of failures. To triage the failures, we had a team of engineers identify errors that were causing the most number of failures. All errors were logged into a Hive table for easy analysis. The engineer would then fix the error and potentially also implement a failure handler to prevent other jobs into running into the same issue. We would then reset the job and rerun them through the state machine and repeat the process for the new errors. This process was done until all the jobs were migrated. One thing to note is that AMS is only really useful for DML queries. It did not make sense for DDL queries to run through AMS, as many DDL queries are just metastore operations that do not consume a lot of resources. The runtime of these queries are also negligible. In order to migrate the DDL queries, we made sure that the DDL statements behaved the same as Hive, and the syntax worked on SparkSQL. If this was the case, the DDL query was automatically migrated over to SparkSQL, and in total, it only took us 2 weeks to migrate all the DDL queries over to Spark. So once Spark was stable and we had a good number of Hive jobs running on SparkSQL, we decided to stop the inflow of new Hive jobs. For ad hoc use cases, we disabled the ability to run Hive except for users who had queries that didn't work on SparkSQL. For scheduled jobs, we built an allow list that contained a workflow job pair that was allowed to run on Hive. And during execution, a check was made for the Hive job, and if it was in the allow list, it would run on Hive. Otherwise, it would run on SparkSQL. Another challenge we ran into was UDF support. For the most part, UDFs worked fine on SparkSQL. However, there were some UDFs that didn't, and the fix required needed to work on both Hive and SparkSQL until the migration was completed. Some UDFs had small changes, and we could get away with making changes within the same file. Other UDFs were very complicated to change, and they needed to be duplicated and rewritten for Spark. And what we would do then is use AMS to automatically convert the UDFs at runtime. Some examples of changes include making the UDFs thread safe. For example, MapReduce and MapReduce jobs, each mapper and reducer is in a separate JVM. But in Spark, two tasks can share the same JVM when the core count is greater than 1. So this caused a previous code to break because of the assumption that the JVMs were isolated. Some UDFs also used the MapReduce context to grab config data that were set through set statements, and we had to rewrite these UDFs to use SQL conf instead, as the MapReduce context is not available on Spark. So after the Hive to SparkSQL migration was completed on AMS, we had to work on migrating the code over to SparkSQL. And there's a couple reasons why we wanted to do this. The first reason is that the code is considered the source of truth, and things hidden from the user are confusing. New engineers working on code can get confused to see a Hive job running as SparkSQL if they were not familiar with the automated migration service. Additionally, query changes over time may lead to failures in the Hive to SparkSQL translator. Final reason is that we don't want jobs going through AMS indefinitely, as it is a maintenance overhead for the team. So here's an example of what we want to accomplish for the code migration. Queries are defined at Pinterest by importing a specific job type that contains the logic to execute the job on a particular cluster. And the queries are defined within, the actual queries are defined within a variable called the query template. We need to add the SparkSQL job import and replace that inheritance. And additionally, we need to update the query template field with the SparkSQL specific query syntax. So here we change the temp table into a temp view and add a repartition. So how can we accomplish this? One way is through the Python AST library. But the Python AST library has some issues. First, the Python AST parser is considered a lossy parser. Generating code from the Python abstract syntax tree would result in an issue where spacing and comments were not preserved in the output. Furthermore, the Python AST library was never meant to generate code, so the tooling around here is extremely lacking. So libcst, on the other hand, is a parsing library that was developed by Instagram. And libcst is a lossless CST. CSTs, or concrete syntax trees, represent the code exactly and preserve white space and formatting. This library allows you to easily traverse and modify code and allows us to easily go from a CST to code and then vice versa. Using this library, we can now convert our Hive jobs to SparkSQL jobs and the code. So here is the general architecture of the code migration. We first pull all the jobs that are in the migrated state. We find the class definition of that job that is referencing it in the code base. We then apply the libcst transformer to the file that contains the class and also update the query to use the SparkSQL syntax. We then create a diff. The diff is sent to the author of the job where he or she can reject the diff or approve it. And if users didn't reject or approve the diff within 2 days, we would automatically land the diff. Next, I'll be speaking about some of the custom changes that we needed to add to Spark in order to fully support the migration to SparkSQL. So the first change we made was thrift table support. So Pinterest has a number of tables that are backed by a thrift schema. And instead of having the table schema definition defined in the meta store, we use thrift files to describe the schema. This allows us to have a single source of truth for thrift data sets. Otherwise, we would have to maintain two different schemas, one on the metastore and then one in the actual thrift files. A custom survey was built that takes a thrift class as a parameter and uses that to deserialize and serialize the data sets. A change was made in Spark to extract columns from the thrift survey object inspector into a format that Spark could understand. The next change is a common complaint on Spark, and it is that S3 renames are slow. So the way that Spark commits data by default is it will first push the data to a S3 temporary location, and then do a rename operation on job commit. And this rename operation on S3 is actually a copy and paste, and it is very slow. So we updated Spark to use a direct committer that was developed by Ryan Blue from Netflix. The committer begins a multi-part upload on task commit, and on job commit completes each of the multi-part uploads that were started by the task. And committer config was changed based on whether we were inserting into an unpartitioned table or a partitioned table. Another issue we ran into is that some of our jobs were reading data that contained thousands of small files. Data sets with many small files can lead to a myriad of issues. So the first thing is it can have long scanning times from needing to list and retrieve many files. Jobs reading from these tables with many files would create many tasks, and each task has a high overhead. And a large number of tasks also lead to driver out-of-memory errors, as the driver needs to keep track of every single task. You may be wondering why we did not use coalesce hints to solve the issue. The issue is that coalesce does not respect split size settings, and coalesce by default does not balance data across partitions, so you can get skewed partitions. With Hive, this wasn't an issue, as we could use the combined file input format and combine many small files. So we took the implementation provided by Hive for combined file input format and made it work with SparkSQL. The combined file input format respects split size settings, so we do not need to worry about skewed partitions. The next change that was required is a decompression split. So Pinterest has some input formats that are not splittable due to the compression codec being used. And changing the source data to use the splittable compression codec was not an option, as there were many dependencies on the particular compression type that was being used. The way we approached this was to have the input format decompress the file and then generate the splits. A threshold config was added that allowed us to set the minimum size of the file that we would consider decompressing, and the size of the split was determined by the MapReduce split min split size setting. So when the record reader receives the split, we decompress and forward the split start and read until the split end. So we only have to decompress, so we still have to decompress the same file for each split, but the data being processed is only done by a subset of the compressed file. For large compressed files, this is much more efficient than a single task processing the entire file. The last change I'll discuss is MSCK repair table improvements. One of the things we noticed when we started migrating jobs is that a lot of users were rolling back their jobs as they were unable to run MSCK repair table that had bad partitions on tables that had bad partitions in S3. So Hive ignored bad partition paths, but Spark would fail the query when it encountered one. Additionally, Spark will also re-add all the partitions that already existed on the metastore. This overloaded the Hive metastore for tables with large number of partitions and is exacerbated if many tables are repairing during the same time. So we put a fix to avoid adding the same partition if it exists within the metastore. So after the migration was complete, we saw a large dollar cost savings and a runtime weighted speed up of 70%, a 38% reduction in the CPU usage, and a 61% increase in the memory usage. The memory usage is kind of expected as Spark is a lot more memory hungry than Hive. Yep. Thank you, and thanks for taking the time to join this session, and have a great day. And I'll be around if anyone wants to ask questions.
So thank you so much, Zahir. I think we still have some time for questions. So if someone has a question, we can also answer it now.
Thanks for the presentation. I had to deal with this type of challenge with many people. One of the challenges is like a lot of the big Hive queries are full ETL jobs in HQL files. That was a big pattern on the Cloudera Hortonworks world. And fully understanding the intent of what the ETL was going to do was very challenging because you had a lot of temp tables, there were a lot of old style PL SQL type of constructs that people were trying to emulate. So I was wondering if you had that pattern where there were large HQL files with a lot of create tables, create temporary tables, people writing data to HDFS, and somehow if you manage to parse that out, understand the intent of it, because in Spark with data frames and the lineage and actions and narrow and wide transformations, you don't really have to do a lot of the temp table type of stuff. You don't have to, for example, join something, filter it, save it, and then read it again. So did you have that challenge to go through? I'm
sure there were some queries at Pinterest that actually did that, but we weren't too concerned about that. So we allowed the user to have the query do whatever he or she wants. And all we would do is we would just make sure that the queries were safe to run. And then we would validate the outputs of every single statement that was within the query. So we weren't too concerned about how the query was formatted and all the things that it was doing. We were just cared about if it could run on SparkSQL and if the performance and the cost were less than or equal to Hive, basically. Yeah.
So with queries, what you mean is literally what individual statements. You're not necessarily looking at the full intent from start to finish, because I've seen some very pretty nasty looking things.
Yeah.
Okay.
Yeah, exactly. We don't look at the intent of the query. We're just concerned about the output and making sure that the output is consistent between the old Hive version and then the new SparkSQL version.
Okay.
Yeah.
Thanks.
So we still have a few minutes left. Any more questions?
I want to ask about how you gonna use variables. Like we are using so many Hive variables in the SQL queries, Hive queries. How you gonna change? How you used to change this in Spark?
So Hive variables work by default on Spark, so it wasn't much of a concern for us. Yeah.
Okay.
All right, with that, thank you so much, Zahin.